function, like I said, I kind of talked about it in my introduction, but a parent function is the simplest of a family of functions, okay? And we're going to talk about several functions at the same time because like we did with our exploring activity, I gave you 3 different types of graphs to look at, and they pretty much did the same type of thing. A kind of worked a little bit differently depending on the shape of the curve, but H and K all worked the same. So a parent function is the simplest of that family of functions. So usually part of this is to identify the parent function, and so whatever I have listed behind the parent function is what you'll list when you're asked to identify the parent function. So the first and most basic type of function we work with is constant. It's a fairly boring function because all it makes is a horizontal line, okay? And so in order to make a horizontal line, our function has to equal a number. So when you see C here, that's just any number. So f of x equals 2, it's a horizontal line at 2. F of x equals negative 2, it's a horizontal line at negative 2. F of x equals negative 15, it's a horizontal line at negative 15. So it's a horizontal line at whatever number that is. So the parent function, or the most basic function, is just 0, starting at 0, 0. So a horizontal line at 0. And then really the only thing we can do with this is move it up and down. So we don't change its slope, because if you change the slope, then it creates the next function. So like I said, constant function is really kind of the most basic, kind of the most boring function that we see. So we don't work with it a ton, but it is the first family of functions that we talk about. The next one, we go from just a straight horizontal line to a line that has some slope. So we have a linear function. Way back in the day, we wrote this more like this. Y equals mx plus b, okay? But I switched to a and k because that's the variables we're going to use for the transformations. So a here is like the slope. So when you change a, you change the steepness of the slope, okay? And we'll talk about a little bit more in depth. But that's what happened whenever you changed a. Like with our parabola, it widened out or made it more thinner. Yesterday when we were adjusting a, it actually works the same way. So with this one, it's just going to change the steepness of the slope. So either make it more flat or more steep. And then the k is like the y-intercept. And so what that does is it moves it up and down on the y-axis. So with the linear function, there's only 2 things that affect it. Notice there's no h in that. And then the parent function for the linear equation is just a plain x. So when you do plain x, that means the y-intercept is at 0 and the slope is 1. So that's the most basic line that we talked about. Okay, ready to go to the next page. Next one is quadratics. We worked with this one quite a bit already this year. We did a little bit of graphing with it in the first chapter. We've talked about it. It was in our activity yesterday. But in order to be quadratic, you have to have a squared in it. So that's why the parent function of a quadratic function is just x squared. Because what makes it quadratic is it has a degree of 2. And then if you'll notice, next to quadratic function, I have where the a, h, and k will go. And like I said, this is kind of what I had to type in yesterday into decimals when we were exploring that. So the a goes in front, it's what's being multiplied. H is subtracted in with x, and then we have the squared on that, and then the plus k goes outside of that. The parent function for that, like I said, is just take out a, h, and k, and so all we're left with is x squared. And so the reason why we identify the parent function is because this is the most basic, most simplest form of this family of functions. And so then when we put numbers in and around the x squared, then that's what makes the graph transform. So it makes it move left, right, up and down, change slope, different things like that. Then cubic function is very similar to quadratic. The only difference between it is instead of an x squared, it's an x cubed. And then the curve makes it a little bit different. Okay, cubic functions, a little bit more of a nice smooth curve. Parabola makes more of a U shape. But same idea. What makes it a cubic function is you have a cube. So when you see a cube, you know that you can identify the parent function as just x cubed. And then we put the a, h, and k in it to transform it either move it left, right, up and down, change the slope, different things like that. Questions on the first four? Everyone got all the blanks filled in? Square root function. We were supposed to do more of this last year, but pandemic and all that. But this is a square root function. Basically, it's kind of a half of a sideways parabola. That's why it's just kind of only a little bit of a branch of a graph. So this one's pretty easy to identify as a square root function because you see that there's a square root in it. So then its parent function is just the square root of x. And you should notice that trend with parent functions is basically just whatever makes it that type of function and just x. So what makes it just linear is it just has an x, no other fancy things with x, except for maybe some numbers, but parent function for linear is just x. Parent function for quadratic is just x squared. Parent function for cubic is just x cubed. Parent function for a square root of x is just the square root of x. Okay? And then, like I said, you can put numbers in, out of the square roots. So your a is always multiplied. So since it's being multiplied, that's why it changes the slope. We'll talk more about that specifically here in a second. And then can be numbers added or subtracted inside the square root or outside the square root. And whether they're inside or outside affects how it moves the graph. That's a square root function. Then we have a rational function. The reason why we call it a rational function is because the x is in the denominator. And when we talked about groups of numbers way back when, the rational group is when we have the fractions. So that's why it's called the rational function. So we have x in the denominator. Where this one looks a little bit different because that x is down here. So our a is whatever the top number is. And so if our top number is just a regular slope, it's 1. So that's why the parent function for this is 1 over x, because we have to keep x in the denominator. And so if our slope is just 1, it's just kind of the basic slope of any function. And then as you change that number, it changes the slope of the graph. Okay? And then h, what you'll notice about h, it's always either inside the function or right next to x. So the h is going to be subtracted in the denominator. When we do that, and we'll talk about what h does, again, we've explored that a little bit, and then the k is added behind the fraction. So that's rational functions. And we got one more family of functions. So we have 1, 2, 3, 4, 5, 6, 7 different families of functions that we're going to work with. Okay, so we had constant, which we won't see a lot happen with, linear, quadratic, cubic, square root, rational, and finally absolute value. Again, because it's an absolute value function because it has an absolute value in it. Okay, so it creates a little bit different of a graph. Absolute value graph is a V shape. And again, you put the a, h, and k in and around the absolute value. So a, like as you'll notice with all of our functions, a is always multiplied in front. H is always added or subtracted inside of the function. So here it's inside the absolute value, or it's in the square root, or it's inside the parentheses of the square, inside the parentheses of the cubic, and then the k is always added behind the function. And again, what makes it a parent function, take all that out, and it's just the absolute value of x. And so when I ask you to identify parent functions, like I said, take out all the numbers and just leave the operation with an x. So since it's absolute value of x is its parent function, and that is the V shape. Okay, questions about the parent functions? We haven't really done much with it yet. We'll talk about what we're going to do with it in here in a second. The other thing, I also provided a graph with each one. Sometimes you might be given a graph and identify the parent function, so I tried to give you just a snapshot of what those graphs would look like. So that way, if I give you a V graph, you know that's an absolute value. Okay? Or I give you one that has 2 little branches, it's rational. Okay? Ready? Alright, this next one, I was just going to have you look at Desmos. What I did is I went ahead and snipped the graphs here, it doesn't worry about. So we're just going to compare these graphs. Hopefully you can see this. So whenever we're asked to describe the transformations, which is what our direction typically is, what it's asking you to do is compare to the original parent function. So that's why we always identify the parent function first, and then we describe the transformations. So this one, I've identified my parent function as x squared. So So that's what the red parabola is. So that's the most basic function that we have when we're talking about quadratics. So it's a parabola that goes to the origin. Okay. Then what I did for the second graph, or the blue graph, is I put some numbers inside and outside of that square. So when we look and compare the red graph to now the blue graph, you can see that it's moved right and up. How much did it move right? 5. And then how much did it move up? 3. Yep. So that's why H affects how it moves left and right. So because I put the -5 inside of the square, that made the graph move right, and then it moved up 3. Now, what the tricky thing is, if you notice, it's x -5, so you think it might move left, okay? The horizontal movement's actually opposite what you think, so we'll talk about that next. That too much information at once. Yeah. So whenever I ask you to describe the transformations, there are 3 types, okay? We have translations, which is actually 2 types of translations. We'll talk about reflections, and we'll talk about dilations. So the translations is a horizontal or vertical shift of the graph, and that's based off of the numbers that you're adding either inside the function or outside of the function. So there's technically 2 different types of translations, a horizontal shift or a vertical shift. So the vertical shift is controlled by that K value. That K value is what shifts it up or down. So when you list this particular transformation, I want 2 things. I want you to say the direction and then how many. So with this one, if you're looking at K, like I said, it's added outside of the function. So that's why I put f of x plus k here. So it's the number that's behind everything that's added or subtracted. So if that number is positive, so if k is bigger than 0 or it's positive, that shifts it up 3. Which you'll see with my little snip that I did for that last slide, that plus 3 made the blue graph go up 3 units. Now if I made it negative, what it would do is it would shift it down instead. So if it was -3, it would have gone down 3 instead of up 3. So if k is negative, it shifts it down. So up, positive, down, negative. That's straightforward, that makes sense. It's when you shift it left or right that it's kind of backwards what you think. Okay, usually you think negative left, positive right, but as I showed you, I'm going to flip back real quick with that snip that I put up here. Notice it was x minus 5 inside of the function, but notice the direction it shifted was to the right. Okay, so whenever you're doing left and right, it's opposite of what you think. So it's going to go left when h is positive, and it goes right when h is negative. And the reason why that is because when the initial function is set up, notice it's always x minus h. So since the original setup of all of these functions started off with a subtraction here, if it wanted to go right 5, put 5 in there, then it's going to look like x minus 5. But if you wanted to go left, and put left -3, put -3 in there, that's going to switch it to a positive, okay? So that's why it's opposite, because the way the functions were set up was it's a subtraction there originally, so whatever number you plug in there changes sign. So, does that make sense? So the nice thing is that instead of having to look at the graphs each time to see how much it's moved, once we know that these 2 numbers, what they do is if you're adding something behind, it moves it up, subtracting something behind, it moves it down. If you're adding something inside, it moves it left. If you're subtracting something inside, it moves it right. You can actually look at the equation without having to look at the graph at all and tell me how much it's moving left, right, up, or down. there's usually two parts. Identify the parent function. You're going to identify the most basic that you have. And the reason why we do that is because it gives you a basis of comparison. Because the parent function will have no numbers in it. It'll just have the basic, what makes it that type of function, and an x. Okay? And then you're going to describe the transformations. So for this one, right now we're just talking about moving it left, right, up, or down. So whenever you're talking about that, again, I need the direction and how many. And for this particular example, if you notice, they're all based off of the same function. So I'm just going to do part A for all three right now. What type of function is this? When you see those bars like that as absolute value. So what's the parent function for absolute value? Okay. So it's just f of x equals absolute value of x. So there's my parent function. And like I said, usually I have you do it for each individual example, but if you notice, each one of these is the same parent function, so I'm just identifying the parent function for all three right now. Okay? Does that make sense? So now that I know that this is the most basic of the absolute value functions, it helps me identify, okay, these two numbers are making my graph move somehow. Okay? So for part B, to describe the transformations, I need to describe the direction and how many. So if it's inside the function, that's where h lives. So what's that 5 going to do?
Move it
Move it to the right.
Right? 5. Yep. So we're going to say right 5 units. Because of that 5. And then what does the 3 do? Up 3 units. Yep. So if I looked at this graph, instead of having a V that goes through 0, 0, I'm going to have a V that's moved right and have 3. So you can look at the graph just to confirm that. But now that we've studied enough with the exploring activity yesterday, and then that little quick snip I did before, that we know that's going to be true. So you don't even have to look at the graph to tell me how much it's moved. Okay. You don't have to have 2 movements, you can just have 1. So what's the second one? Down 4. Yep. So notice the 4 is outside of the function. That's really how you can tell whether it's h or k. So if it's inside, it's h. If it's outside, it's k. So k moves it up or down. This is it's negative. It moves it down 4 units. And then what about that last one? Left 7 units. Yep. Make sense? Okay. Let's do another one. This one's, I really like absolute value because you can really distinctly tell if it's inside the function or outside the function. Sometimes, so I'm going to do a second example of this before we go on to the next transformation. Sometimes it's not quite as obvious. So what's the parent function for this example?
X cubed.
X cubed. Yeah, because it's cubic. So my A, f of x equals just x cubed. Okay. So is that with that first one, is that 5 and h or an k? It's a k. Yep. So this is where you can tell it's inside or outside the functions based on whether or not it has parentheses. So notice this one has parentheses, so that's one that's inside the function. So if it's inside, it's h. If it doesn't have parentheses, that means that's a k, so that's going to be an up or down movement. So that's going to be a down movement. What's the movement for my second one?
Right 3.
What?
Right 3.
Right. Yep. And this last one has 2 different movements. What's this?
Left 2.
Yep.
Up 4.
Questions about the translation and transformation. So translations, we move the left, right, up. Okay. now we're gonna look at the second one. The second one's very subtle. Okay, if you notice when I had you play around with A yesterday, there's actually a couple things that happened. One of those things I wanted you to see is what happens if we put a negative in front of the function. I actually get a second one here. So here the parent function was x cubed, and all I did was make it negative. So if we compare the lines, so the original one is my green line. That's why I snipped that so I could remember which color was what. Okay? And notice the second one, just by making it negative, is now, notice how it kind of goes opposite direction. Okay. And then I did another one because it's really easy to see with like an absolute value or a quadratic graph. So notice the black one is the original absolute value, and then all I did was make the absolute value negative, and then what happened to the graph?
It flipped.
It flipped. Okay. So what that's called is a reflection. Okay. So it's a reflection. Technically, officially, it's about the x-axis. So if you look here, so the green was the original. By making it negative, this one now flipped over the x-axis. Again, the original was green. By making it negative, it flipped over the x-axis. So by making it negative, no numbers, just the negative makes it flip or makes it reflect. So it's a reflection, which is a mirror image of the graph with respect to a specific line. And our specific line for our graphs is the x-axis. And that's the only type of reflection we see. So it's a reflection about the x-axis, or just, since that's the only reflection, we say reflection. So whenever you see a negative in front of it, again, doesn't have to have a number. The number actually tells us something else. It tells us something about the slope, not necessarily the position of the curve. So as long as there's a negative in front, that tells us it's a reflection. Okay? So what's the parent function?
X squared.
X squared. Okay. And then my transformations, there are two things. So if you look, my parent function is x squared. So I notice there's two things that are different from the parent function. So that means I have two transformations that I'm going to list. What does that negative tell us? It's a reflection. Yep. So it's a reflection. About x. Okay. So I'll write it out officially, but like since this is the only reflection we have, if eventually you want to cut down some of the writing, if you don't write about the x-axis every single time, that's fine, but just know that that's what it is. Okay. Is that okay? And everyone knows why we wrote reflection? The negative, yep. So then, what does that plus 5 tell us?
Up 5.
Up 5, yep. So this parabola would be flipped upside down, and then it would be up at 5. So if we were to look at the graph, it would look something. So it's the reflection, so it flipped it upside down, so it's no longer facing up, and then it moved it up 5. So that's what this graph would look like, and we don't even have to look at the graph. Questions about reflection? That's the most subtle of the transformations, because it's not even a number, it's just a sign. So the sign on in front, if it's negative, that makes it a reflection. Okay? Now, if there is a number with the negative, then that makes it something else. Okay? So it's a reflection and this next one. So what I did here, I tried to pre-snip it so I don't have to keep going back and forth between decimals. So with this first snip I have here, and I listed all of them. So the black curve is the original absolute value V shape. And then what I did with the red curve is I put a 5 in front of the absolute value. Okay? So this is the original, and then this is with 5 in it. What happened? Get smaller. Okay. So it changed a little bit of its slope. It made it steeper slope, or it made it expand, so that instead of being out here so wide, it's now pretty thick. Okay, what we call that is an expansion. And so really what it is imagine taking the ends of your absolute value and pulling them up. Okay, so you're expanding it vertically, you're pulling up the slope so it's a lot steeper. Okay, so that's one way the number in front of the function affects your graph. The other way is, notice now I put a 1/3 in front of it. So now the black graph still is the original absolute value, and now the blue graph is what happens when you put a 1/3 in front of it. What happened there?
Got wider.
Got wider. Okay, flattened it out. So imagine taking the absolute value and pushing down on it. Okay, it compressed it is what it's called. So because what we're doing is changing the slope, we're making it flatter. So we kind of compress the graph. So push down on the top of that original function, and it widens out. So we compress vertically. So those are our two choices. You either expand it vertically, where you stretch it out, or you compress it vertically and push it down. So what that is called is dilation. And like I said, we don't actually officially ever use the word dilation, but that's what the technical transformation is called. Just like we don't ever really use the word translation, because translation means you're moving left, right, up, and down. But dilation, what we use is we're either compressing or expanding vertically. So you're either going to compress vertically, expand vertically. Those are our two options. So where this comes from is the A value. So notice in big asterisks, I have ignore the negative, okay? Because the negative is something totally different. It's separate from the number because the negative tells us reflection, and that's it, okay? Other than that, if it's a negative or a positive in front of it, it's actually going to do the same thing. It's just the negative is going to make it flip upside down and then expand or compress based off of the number. So just ignore the negative, because the negative tells us the reflection, and then the actual number that's with it tells us whether it expands or compresses. Now with this one, notice we're comparing it to 1, and the reason why that is because A is being multiplied to your function, and so yesterday with our exploration, if we made it 0, it just made it a horizontal line, okay? Because if you multiply anything by 0, it's going to get rid of it. So that's why with dilation, what we're doing is comparing it to 1. So our most basic slope of any graph is 1, because it's rising or running at a similar rate. Nice, easy slope, because that's really what we're affecting. So basically you're going to look, is that number bigger than 1? Again, ignoring the negative. So this could be 2 or negative 2 does the same thing. So if it's bigger than 1, it expands vertically. Now, what else also happens, and I could make you write this too, if you ever expand something vertically, like imagine taking like silly putty or whatever, I don't know what else to think of right now, but if you pull it up, you're expanding it vertically, what happens horizontally is it gets thinner, okay? So I could have you say expands vertically and compresses horizontally, but I choose just to have you do the vertically part, okay? So what we're doing is taking the graph and just pulling it up. So it is going to make it thinner horizontally, but it's also going to make it taller. So it's expanding vertically. And then for compressing vertically, that's a very narrow window of when that's going to happen. So we actually don't see this one happen as often, but it has to be numbers that are in between 0 and 1. Okay? So like 1/3 or the 1/2 or something in between. Usually it's some sort of fraction, but that's going to compress it vertically. So what that happens there, imagine taking like a balloon or something, and you take it and you push down on it, okay? So that's going to make it not so tall. It also widens it at the base. So I could have you say it compresses vertically and expands horizontally, but what I'm choosing to have you do is just tell me what it's doing vertically. So is it extending out vertically, or is it compressing vertically? So if it's bigger than 1, it expands vertically. If it's in between 0 and 1, it compresses vertically. And again, make sure ignore the negative. So whether it's 5 or -5, both of those those are going to expand vertically. Because the negative just means it reflects, so instead of having a parabola that faces up, it's going to face down, but it's still going to expand vertically, just downward. So let's do some more examples. And then we're almost done. What type of function is this one? Whatever. Yep. So the rational function, because again, whenever you see x on the bottom, our parent function for this is 1 over x. Okay? So that's where it becomes kind of important that it's 1 over x. So now I can see there's actually two things that have changed from my parent function. There's now this 3, and there's this plus 5. So however many things have changed from my parent function will tell me how many transformations I'm going to have to do for this particular problem. So there's going to be 2. So this number is the a value, okay? So that's going to tell me if it expands vertically or compresses vertically. So is that number bigger than 1 or in between 0 and 1?
Bigger.
Bigger than 1. So that's going to be expand vertically by 3. And usually when we're telling, except for with reflection because it's not really a number, I usually like to tell me the number that it's coming from. So it's expanding vertically by 3. Okay? Now what does that 5 do? Up 5. Questions about that one? What about the second one? What's my parent function?
Square root of x.
Oh, you don't always have to write this f of x, that's just a habit of mine. As long as you have the square root of x, I'm fine with that. So then, comparing it to the square root of x, I see 3 changes. There's this negative, there's this 3, and there's that 7. So there's 3 transformations I'm going to say about this function. So what's that negative tell us?
Reflection.
It's a reflection. Yeah. Again, technically reflection about the x-axis, but I'm okay with stopping at reflection. Everyone okay with that? Okay. What's that minus 3 telling us?
An expansion.
Right, 3. Yep. So since it's being added or subtracted, whenever you see addition or subtraction, it's going to move it left, right, up, or down. So since this is inside the function, this is a horizontal movement. It's opposite what you think. So the 3 there is going to move it right 3 units. Okay. And then what about that 7?
Up.
Yep, up 7 units. So that one didn't have a dilation, because again, if you look in front, it's just a negative, there's no number. So I knew it didn't have an expand or compress, okay? So it's only expand or compress if you see a number other than just a negative. Okay, next one. What's the parent function?
Absolute.
Yep, so it's absolute value of x. That is bad. Okay, so what I see, there's a negative, there's a number in front, there's a number inside, and there's a number outside. Okay? This one has the most transformations you can ever have. Okay? So the most things you have is all 4 things affect. You can have a reflection, you can have expand or compress, you can have left or right movement, you can have up or down movement. So that is the most you'll have in one problem is 4. So what's the negative tell us? Reflection. Okay. 1/4. again, remember, ignore the negative. We're just leaving it as 1/4. That's going to be one of our expanding or compressing. So you have to look and see, is 1/4 bigger than 1 or in between 0 and 1?
In between.
In between 0 and 1. So if it's in between 0 and 1, it does what vertically?
Compress.
Compresses. Yep. So compresses vertically by 1/4. And if you can spell that right, compress, because I can't spell this thing. Compress. Spelling. Okay. If you want to abbreviate those words, I'm fine with that. So you can do like convert by 1/4. So it's okay if you abbreviate because I know that's a lot to write for one thing. Then what's next? Left 5. And then finally, what's that minus 3 do? Down 3. Like I said, that's the most you'll have for one problem. Let's do the last one real quick, and I'll be done. What's our parent function for this one? Yep, x cubed. So we have 1, just 2 things. So what's that 1/2 tell us?
Compress.
Yep, it's going to compress vertically. Okay, and then what's that minus 3?
Right.
Right. What? Okay. So you just have a worksheet. We'll have some time in class tomorrow to work on this. I'm gonna stop the video. Sorry about the spelling.